In this scenario, our focus is on the automatic research and development of evolving models in quantitative finance. This model illustrates the process of hypothesis generation, knowledge construction, and decision making as we build and refine models using the QLib platform with RD Agent. Let us look into one example here. The process begins with a key observation. Financial market data is typically time series in nature. This leads to the initial hypothesis that a GRU-based model with 3 layers could effectively capture the complex temporal dependencies within the data. Then, the evolving coder starts to implement. Upon implementation, challenges arise. Specifically, the model's forward method fails to generate output, indicating issues in the architecture. Additionally, dropout layers which are essential for preventing overfitting are missing after each GRU layer. These issues are addressed as the evolving coder evolves through each iteration. In the end, the model is re-implemented correctly. The model then goes through this stage of evaluation. Although one could see from this data here that the overall metrics are weak, it does achieve a positive ICIR of 0.115. And that indicates some good potential here. This also suggests that while this model can predict, it has also potential of improvement. And that's where RD agent starts to observe the problems, give an evaluation, and think overall it has potential, so decision is true. But we have reasons here for supporting a new hypothesis. Given this result, the next hypothesis is generated upon the suggestion. One could see that the next hypothesis is to maintain the 3GRU layer, but to introduce a leaky ReLU activation function. This adjustment aims to enhance the model's learning capabilities, potentially improving return metrics while maintaining or even increasing the ICIR. However, as one could see in the second iteration, the model development stage failed completely, in a way that, say, even in the 7th stage, there are still problems. That's what prompts the system to revert to the previous experiments for re-implementation. This time, in the third iteration, things are successfully implemented, but one could see that there's actually a sharp drop in performances across the board, across different metrics. RD agent then gives feedbacks on this hypothesis and points out where things could be wrong, while giving a decision of false, which means that the knowledge is not retained. In the fourth iteration, given these results, what we do is that the model is actually refining its approach further. One could see that they decide to replace leaky ReLU with standard ReLU functions, activation functions, and switch from batch normalization to layered normalization. This new configuration is designed to provide better stability and faster convergence, particularly in the context of time series data where relationships between time steps are critical. The feedbacks reveal that the performance metrics such as returns and risks have improved, and the information ratio has shifted from negative to positive values. This positive feedback confirms our revised hypotheses, and adjustments have enhanced the model's performance. Now, we have achieved a stable and improved model, but our loop and our process doesn't really stop here. The cycle of learning and refining and iterating continues. Each loop not only improves the model but also builds upon the knowledge gained from previous experiments and iterations. This dynamic process allows RD Agent to continuously optimize models, making it an invaluable tool for research and development, say in this area of finance. In summary, this scenario demonstrates the power of RD agents in evolving models through iterative feedback and knowledge construction. By continuously learning from each iteration, RD agent refines its approach, ultimately leading to models that are both accurate and robust, perfectly adapted to complexity of financial data.